Okay, so we said that we will talk about motion of the dislocations, and we have earlier also mentioned there are two basically different types of motion. One is glide, which is also called conservative, and the other is climb. So, in this particular one the dislocations move on surface containing both line vector, let me write it as line vector and Berger vector. In this particular case, dislocations move out of the glide plane. So, this is perpendicular to B. Now, when we talk about glide, for edge it will have different meaning, for screw it will have different meaning. For edge dislocation it would mean that there is one unique plane. We will come back to this concept again. So, there is only one unique plane because U and B they are perpendicular to each other, which means that the plane containing this would be unique. So, one unique plane on which glide takes place. For screw, at a particular time it will be moving on one particular plane, but it can also change to other. Why? Because here U and B are in the same direction. Therefore, there is no unique plane which contains U and B. So, there are several possible planes onto which screw dislocation can move. Only that it has to satisfy certain criterions which we will see later on. So, there is different meaning of glide, but for edge dislocation as we can see there is only one plane, and this will help us understand the concept of lattice movement. Now, that we are talking about one unique plane. So, let us see what exactly does it mean by movement and where does this resistance comes from. Since it is talking about one unique plane, we will be able to explain it better in these terms. The same concept can then be extended to the screw dislocation. So, let us see what exactly we mean by resistance to dislocation movement. So, the resistance, so we will be talking first with respect to glide and glide of edge dislocation. So, resistance to dislocation motion can be associated with two different aspects. One is related to size of the core and the other is related to what we can call as lattice resistance. So, size of the core, so far we thought that there is a particular size of the core, we had defined it, but those were just simplification. In reality, when you look at the structure, the core size can be understood in terms of how much strain it is experiencing. So, for example, there is something called as width of the core. What is width of the core? It is defined as distance from center, the center of the dislocation, over which This is our older definition over which linear elasticity does not hold. And we had earlier said that this is approximately equal to 10% or equal to b by 10. So, if our b is the Berger vector with respect to which we are calculating the strain, so the 10% of this will be b by 10. What does it mean physically? So, shouldn't this imply that everything will have the same core radius? No, we will see here. Let us say again we said that edge dislocation would be easier to understand, which is why you will see here. So, you see where is the dislocation? The dislocation is over here, right. And if you look at the strain just below the plane, then the strain can be depicted like this. Let us talk in terms of displacement. So, displacement with respect to B, which is the strain value, and as you can see the strain is continuing all the way up to this point. So, let us say this is somewhere over here where you are getting 10% value. So, this is like this. So, up to this much distance is your core. On the other hand, I would like to draw it over here, so that the comparison is easier to make. So, let me draw it. Over here. So, here also we will draw the same dislocation, but what you will see is that the strain is limited in a much smaller diameter. So, again where do we have the dislocation? Over here, but if you see the lines over here, they have already acquired the original shape. So, there is no more strain at these positions, and what we have is, if you now draw the strain values, what you have is something like this. So, this time the strain or 10% strain, which is what we are interested, which is where the linear elasticity does not hold, is limited to a much smaller region. So, let us call it W1, let us call this W2. So, what we see here is that clearly W1 is greater than W2. Now, the width of this dislocation is larger, the width of this dislocation is smaller, and because of this their movement would be severely different. They will be completely different on how this dislocation moves, which has a, so this has a wider core, this has a narrower core. And you would expect that the one with the smaller core would move easily, but that is not the case. The ones the dislocation which have a wider core, they are the ones which move more easily. So, these move more easily, movement not as easy. So, this is one aspect of the resistance to dislocation motion. Like the other one we said is the lattice friction or lattice resistance. Or this is also called as Pearl-Nabarro stress. So, in this particular case what Pearl and Navarro found was that the dislocation energy changes with position. Now, if you remember again, if we go back to our dislocations over here. So, this is the dislocation core. If it has to move from this point to this point, this particular layer of atom has to now shift to the left, and this one which is a hanging one, this will be get connected, this will become the hanging one, and therefore, there is a kind of motion that has to take place where from one connected column to another disconnected column, or one disconnected column to another disconnected column, and this would look more like this. So, this will have, if you say this is your planes. So, this is the disconnected column. At one point it will be, both of these will be disconnected, and there is atom over here. So, now this is not connected, or this is in motion where neither of these are connected, and then finally, since it is moving in this direction, finally what you will have is, so there is a transition. So, earlier this dislocation was between these two planes, now this dislocation on the left side it has 3 planes, on the right side it has 1 plane. So, this dislocation has travelled, and in travelling it experiences a condition like this where it will face the largest resistance. So, there will be a energy maxima. Therefore, the total energy of the dislocation is changing, the core energy is changing, and with respect to position. This is what Pearl and Navarro showed can be seen like this. So, this is what this plot is showing, is the change in the dislocation energy with respect to position. And this has to be cyclic, because it is the same structure repeating again and again. So, here you can say this has the lowest energy when it is disconnected. At this particular point it is something like this where it is not connected with any of the atoms, and then again in this position where it is again disconnected at, or it has moved to another local minima. So, it is the lower energy position over here, and this gap or this change in energy is represented as EPN. And therefore, since there is a change in the energy of the overall dislocation with respect to position, so there will be a stress required in moving the dislocation from here to here and then back to here. So, minimum this much stress. So, if we take the derivative of which they have done, they have shown that EPN can be shown something like this. And from this they have derived that tau Pn, which is the stress. So, the stress would also be cyclic like this, since the energy is like this. So, the stress would also be like this, which is the derivative of this. So, the stress would be highest somewhere in between over here, and it will be lowest when the energy is again one of these other position where it is at minima. So, the tau Pn would be is derived to be shown as this, and this is showing you the maximum energy or the amplitude. We have not shown the cos term over here which would exist. We are just looking at the amplitude component. So, this is the tau Pn or the stress, the minimum stress that must be applied if the dislocation is to keep moving, meaning if your stress is less than this, then it will not be able to cross the hill, and therefore, dislocation will come back to its original position and it will not move on any further. and if you are applying a stress which is continuously higher than this, then the dislocation can keep hopping like this, one point to another point and so on, and therefore, the movement of the dislocation can take place. Now, what is the effect of width? We said that width will also make a difference. We will see over here. Let us say width tau Pn. If width is 0, then you will have to apply a very large shear stress. If you increase the width to just 1 b, meaning 1 atom, it already reduces to g by 400. If the width of the dislocation becomes 5 b, so what we showed here as 2 and 3 lines, now we have, if you extend it to 5 b, the stress required or the resistance to move the dislocation reduces by orders of magnitude. So, here it is of the order of 10 to the power 3 and here it becomes g by 10 to the power 14. So, 11 orders of magnitude smaller stress is required if your width becomes like this. And it goes without saying that when you go to 10 b, it will become even smaller. So, which one will move easier? Obviously, this one, it will be much easier to move this one, because the peak or the highest resistance in this particular case is much smaller. So, much easier to move. And this one is much difficult to move. So, the peak is very large here and the peak is very small here. And I cannot even draw the magnitude that we are showing here. So, peak will be like this. Over here the peak would be a very it is nowhere comparable to the scale over here, because it is g, this is g by 10 to the power 27. So, it is 27 orders of magnitude is smaller. So, this is as small the stress required for the resistance. So, the stress required would be as much smaller. So, it is much easier when you have wider core. So, that is the effect of geometry of dislocation on motion of the dislocations. So, let us summarize. It is easier to move wider dislocations. Another aspect which was not mentioned earlier, we had used the term W, which can also be written like W A by 1 minus nu, where A is planar spacing. Now, this W, it is in the exponential factor. Therefore, what we want is that the planar spacing should be largest. If you go back to the equation over here, you want W to be very large for tau Pn to be small, and for W to be very large, A must be very large. So, this is also giving you information about what particular crystal with respect to crystallography, which are the planes or directions where dislocations would like to move. So, what it is implying is that slip on planes with widest interplanar spacing will be easier, because W is equal to A by 1 minus nu, which is where A is the planar spacing, and we saw from this equation that this is in the exponential minus 2 pi W. So, that you want W to be larger, so that tau Pn can be smaller, and this W will be larger when A is very large, which means that planes with the widest interplanar spacing will be easier. And when will you have the widest planar spacing? When you have the densest planes. So, this implies densest planes will show slip. Of dislocation. So, this factor which is in the tau Pn is also giving us some information about the geometry. Another aspect that you see over here is B. So, this also gives us some information. B is the slip direction. So, we have talked about slip plane, we saw that slip plane has to be the densest plane. Now, B is in the denominator, so this has to be very small. If it is small, then it would mean that this quantity is this negative quantity is large, and therefore, tau Pn is again small. So, for B to be small, we know that B should be small. Where is the B smallest? Thus, B smallest along direction with shortest lattice vector, lattice translation. So, B is small in the shortest where we have the shortest lattice translation, or implies where you have the closest pack direction. So, based on this tau Pn, or when we talked about the resistance to lattice movement, we saw that there are two components. One is the core size, we said earlier that larger core size will move easily, smaller core size would move with more difficulty. That is one aspect, and the second aspect was the lattice resistance, which gives rise to tau Pn, and the size of the core has direct relation on the tau Pn. Now, we also have the equation derived by Pearl and Nabarro, what should be the tau Pn, and from there we see how the crystallography of the material can we can get more information about the crystallography or the directions of dislocation movement with respect to crystallography of the material. And what we saw is that A, which is the interplanar spacing, should be very large, and for that it means that we have to have densest plane. B should be small, which means again it should have the densest direction. Now, now that we have this information, let us try to look what they would mean for two of the simplest system. One is the FCC and the other is the BCC. So, what we are looking for is the planes with largest interplanar spacing or the densest packed planes, and second we are looking at the closed packed direction. So, first let us look at FCC. Let us look at three important planes which are low indices planes, where we would expect something to happen. So, let us compare these different planes. If you look at the FCC atom, FCC cell, so this is how the FCC atom would FCC cell would look like, and here let us what we are looking at 111 plane. So, let me draw the 111 plane. So, this is one of the 111 planes. Similarly, you will have another 111 plane over here. So, this is one plane, there is another plane, and of course, at this particular location you have starting of one another plane, and this particular location will lead to another starting of the plane. So, in this let us take about one this particular plane, how many atoms do we have? First let us look at the number of atoms. So, for this particular plane you can see that the number of atoms will be equal to 2. Next what we want is atoms per unit area, because this is what will give us the densest plane, atoms per unit area. So, this is 2 atoms, and if this is the A root 2 and this is the equilateral triangle, therefore, the area would be root 3 by 4 A root 2 square. So, this will be 2 divided by root 3 by 4 A root 2 whole square, which will come out to 4 by root 3 A square. And since it is lattice parameter, so we can write it as A naught. So, this is A naught, and similarly at the same time let us calculate what is distance between the planes. Now, this whole distance from this point to this point is equal to root 3 A root 3, and there are how many planes? There are 3 planes. Therefore, this distance between the planes can be written as root 3 A by 3. So, it is again A naught by root 3. For 100 plane, again this is very easy to see. This is 100 plane. How many atoms are there? 2. What is the number of atoms per unit area? So, the area is A naught square. So, 2 by A naught square, and the distance between the planes. So, this is one plane, this is another plane, the distance is equal to A naught by 2, A naught by 2. This is now let us look at the third plane, which is 110. So, this is the 110 plane. Again you can clearly see that there are 2 atoms here, and the area of this is equal to A naught square root 2. So, this becomes 2 by root 2 A naught square equal to root 2 by A naught square, and the distance between the planes is equal to from here to here, which is equal to A naught by 2 root 2. So, now looking at this, which one is the largest atom per unit area, and we can clearly see that this is the largest value 4 by root 3 A naught square. This is the smallest atom per unit area, and which is the largest distance between the plane. This is the largest distance between the plane, which is A naught by root 3, because this is the smallest denominator. So, this is the largest distance, and this one comes out to be the smallest atom per unit area. Therefore, in FCC 111 has the largest distance between planes, which implies largest atom density. So, yes, again I take back what I said earlier, that this will become the largest atom density. So, 4 by root 3 is greater than 2 is greater than root 2. So, this is the largest atom density plane, and therefore, 111 is the slip plane for FCC. So, what we have calculated here is number of atoms, from that we have calculated atom per unit area, and from and we have also independently calculated distance between the planes. What we find is that distance between the planes for 111 is largest, meaning they are at the farthest distance apart. If they are farthest distance apart, since the total atomic density has to be inside the cell has to be constant, therefore, the atom density in this particular plane has to be largest, which is what we see 4 by root 3 is the largest value, is greater than 2 is greater than root 2. So, this has the largest atom density. So, this is the densest or it is the densest plane, and therefore, 111 is the plane onto which slip will take place, and for FCC this happens to be this. So, we have already established based on the relation for tau Pn that 111 will be the slip plane. Similarly, if you look at the Berger vector, you should be able to derive, and we will come back to this in the next class. In the meantime, I would hope that you can go back and find what will be the Berger vector for FCC. We have already described the slip plane. So, we will come back and meet here.